Well, the next speaker is Gordon Cheng. He's chair professor and director of the Institute for Cognitive Systems at the Technical University of Munich, and coordinator of the Center of Competence in Neuroengineering. And he will talk about tactile intelligence for robotics.
Thank you, Camille. It's great to be here. Thank you, everyone. And thank you for the organizer for inviting me. And Tamim and everyone doing a great job. So I thought I'd share with you, before I do that, I always acknowledge the people behind this. Okay, so everything I show you, there's a lot of people behind us, and they're great people, and I learn a lot from them. So I just give you a background, and then I'll go into some my obsession. I call them obsession. That I go into different topics. There's 3 different things that I do. I like to understand the human science, which primarily the brain. All right, that's what we spend a lot of time doing. And then the other one that I will focus more on today is improving and also creating better technology through the understanding of the brain. And then the third thing that I will be doing probably for the rest of my career is trying to bring technology to help people. All right, so what do we create all these cool technology for? So let me share with you one early obsession that I had more than 20 years ago. It's quite long ago. So I had the privilege of working with Sarkos and a fantastic gentleman called Steve Jacobson. Right? And we spent about 7 years together just to create the state-of-the-art humanoid robot. So this became the first fully force-controllable humanoid robot in the world. Right. And it ended up to be 51 degrees of freedom, and it was pretty cool. Right. We could do it 30 degrees of those freedom. We could do force control. Right. So that was the state of the art at the time. And as a career advice, I spent 7 years doing this. I published 1 paper, and that's not recommended. So we could do a lot of very interesting things. This is something that we were modeling, in the neuroscience side. We were modeling the vestibular system, which is what tells you about your balancing, how you balance in the world, what is your orientation. So we did all the plasticity control related to this, controlling the force, going in, going out, equalizing them, and then coming up with a fantastic balance controller. Okay, so this was really cool at the time, and there was one thing that disturbed me is that we done the Hamiltonian proof and all that, but we have no idea where the robot is making contact. And then, therefore, I started looking into the issue of touch. And this morning, I think Catherine and Alison have already gave great introduction to touch. That's okay, don't worry. So some of the things that we actually do every day of our life is we use our whole body for interaction. And coming to this conference, I gave a lot of people hugs, okay, social interaction, contact control, right? We use touch phenomenally, and also this issue of classification. And application, there's immense application in the entertainment. Healthcare is something that I will be spending a lot of time on through the rest of my career. And industrial automation, people already asking me about touch, and then sports also been coming around to talk about touch. So this morning, Catherine and Alison already gave the necessity of multimodality, right? So what we decided, or I couldn't find anything I could buy, right? Most of the sensor I can get was on, off, and how much is on, and only usually a single modality. So I said I wanted something that is multimodal. What we decided to support temperature, touch, pre-touch, and vibration, which was highlighted by Catherine this morning, and stretch. So those are the important factors that we wanted to look at. So proximity was one of the things that we actually feel before we touch. We actually sense before we touch. Impact is a vibration, temperature. Right. And it is a very nice way of controlling an industrial robot arm. Okay, so that was the beginning of just creating a sensor that is multimodal. Right. But the actual surface of our body, right, about the whole skin structure, is how to connect all these sensors together to actually make a whole body, how we can actually deal with it. So one of the inspiration that we take is, I think many people know this diagram. It's the homunculus diagram that it talks about the somatosensory cortex, right? It maps out the entire sensory or receptor on our body, right? So we thought that we should create something like that, okay? So we created a 3D reconstruction system that you can actually put arbitrary shape together, right? And then put network together, of sensor together. Then you have a complete 3D reconstruction and localization of your surface of your body. So that's a somatosensory cortex. But there's actually a second factor, right? How do you control your body with all these sensors? Right? So the idea behind this is it's a concept called motor babbling, that we jiggle our body and we learn about how we move and how we act. And that gives us a sensory motor pair that we can actually utilize for control. And this is just one example of that. Okay, so that's an early example that we just throw it on to a robot arm, and then the system just jiggles, and then it learns about the entire sensory motor pair, and at the same time learn about the location of every single sensor. All right. But to actually make these things work, you have to connect them all together. All right. And what we were, sometimes I half joke, I say smash it with a hammer, and I get a video that they smash it with a hammer. All right. And then I said, cut it with a knife. All right. Every time you see a flash, that is a recovery mechanism of the entire network. All right. And the worst case mechanism is actually you smash the individual cell. And the system automatically recover, or it has a recovery mechanism. Right? So this provides us with robustness. Right? That network's dead, and that cell is dead, and then the whole system recover. And the beautiful thing is the recovery rate is at about 42 milliseconds. And so you can actually throw the skin onto any robot arm. That's a vision I had. And then you can make them fully compliant. And this is controlling with a feather. This is Emmanuel Dean working on this. It's very cool. Okay. So that means we provided 3D reconstruction, right, and sensory motor pair, allow the robot to be completely compliant, controllable. Okay, so the obsession that I started with was that I want to cover a complete humanoid robot, right? Any humanoid robot, and it does not have to have joint torque control or any of that, right? And to actually provide full multi-contact control. So these are the two examples I have, and it should be autonomous. So the difficult problem with this is how do you handle all the information? So this is an example that I always show, that the human body have 5 million, at least 5 million receptors. And then if you do the conventional wisdom that asking your body to give you your data, you need a house full of computers, right? A massive amount. So what we did was solving this problem by using something called event-based system, which is very similar to the event camera that you have been discussed already. And what we ended up with, an autonomous humanoid robot with tactile skin on the bottom and all over the body. I think we are doing about 13,000 receptors. And if I do that with the old standard engineering approach, it will fail completely and the control loop would die. And this is just showing that we can actually estimate the DMP for balancing and the center of mass. And unlike the conventional method that rely on joint torque center at the ankle. Right. So this is one example of how you actually deal with local motion. I will wrap up quickly. So this is just showing that if you walk on a plane that is perfectly in the center, your robot will fall with the conventional force torque sensors. And so full body interaction. Okay, so we made the whole robot fully autonomous, and you can actually control it, through interaction. And my favorite bit is, and one of the example we did do the hugging, but I thought we were more interesting to do some kind of dancing. So we decided to do the box step dancing, and Dean is actually a good dancer. Okay, so another example is motivated by how you move in navigation. We apply this to navigation. For example, if you have all of us, when we move around space, right, when the object is movable, we actually move them out of the way. Right. And this is the example of this. We can actually maneuver or steer the object in any direction we want by using contact sensing. Right. So this work was inspired by Mike Stillman and James Hoffner. They did some early work on navigation domain movable objects some years ago. And the robot just go through and try to decide which object is movable and which is not movable. And this is a fairly big robot, so it steers different objects out of the way. Okay. So I'll go a bit faster. So we started working on actually dual arm manipulation and all these, and then we actually looking into multi-robot cooperation now with full interaction. So one of the things that we were doing that surprised us is utilizing the tactile sensing as a sensory substitution for patient. Right. So about 2013, I started flying to Brazil. We created an exoskeleton that allow us to provide feedback, tactile feedback to the patient while they are inside the exoskeleton for walking. And the sensor actually ended up to be working that the patient actually did the 2014 World Cup kicked off with the exoskeleton and brain machine interface to go with that. I want to do this one quickly. So what is surprising for us is that all 8 patients started recovering through all this training. I think this is a very important discovery that we were making at the time to how to actually train patients to help them recover. So for the skin, people keep asking me about the skin sensor. We're making it accessible, and there's a spin-off that came out of the lab, and I think all the license agreement, everything has been signed off by the university now. So with that, I only want to say that I started 2 new projects. One is the new ERC project for soft lower body limb exoskeleton for walking. And then the other one is a soft hand exoskeleton for grasping that we started these new projects. So I'm going into soft exoskeleton. And I'd like to thank all my funding thing. And I thank you for listening.
So we have time for a very quick question. if you have one. I remind you that you can meet the speaker in the speaker's corner and all around, I guess.
Thank you.
So, yeah,
One question.
yeah,
Well, actually, a comment. Gordon, I appreciate being one of the people you'll give a hug to.
I don't.
So that's good. And I appreciate you being ahead of the curve on humanoid robots, but and tactile sensing just over the years. But is there a particular task or particular set of tasks in healthcare that you think your approach to tactile sensing is going to be particularly useful for moving forward?
So the tactile sensing it's a platform, right? The main thing is we use it as a sensory substitution. The concept is when you're paralyzed from waist down, if your spinal cord injured, you cannot walk and you cannot sense. So the paradigm we're using, it's for sensory substitution. And you're right, if we want to go all the way to healthcare, there's going to be a lot of issue with certification, right? And every trial we do now, we have ethic approval, and that takes a year and a half to actually get any of these trials going. Does that answer your question? I don't know.
Yes, thank you, and I'll follow up.
Okay, thank you.
Okay, thank you.